A lot of people, when they learn about string theory for the first time, are taken aback by what a beautiful, powerful idea it is. When we look at our universe and discover the way it is, we find that it follows a certain structural pattern that, for as intricate as it is, seems to follow rules that apply very differently to different components of the theory. We have, for example, unequal numbers and generations of fermions versus bosons, an abundance of matter over antimatter, a universe filled with electric charges but no magnetic charges, and plenty of left-handed neutrinos and right-handed antineutrinos, but none that are the other way around. There are a lot of symmetries that you could imagine would be respected, but simply aren't. You could imagine that the three forces of the Standard Model would unify into a single one at high energies in some sort of grand unification. You could imagine that for every fermion, there would be a corresponding boson, as in supersymmetry. And you can imagine that, at the highest energies of all, that even gravity gets unified with the other forces in a so-called theory of everything. That, according to renowned theoretical physicist Michio Kaku, is the brilliant, beautiful, and compelling idea at the core of string theory.
So string theory is the only game in town which has the ability to be really a true theory of everything.
However, not everyone agrees with Michio Kaku. 2020 Physics Nobel laureate Roger Penrose, a well-respected physicist who co-authored a seminal paper on black holes with Stephen Hawking, has declared that the string theory is a fashion. It is nothing more than a broken box of dreams.
Well, I think the trouble with string theory is that there isn't any connection with observations. As far as I'm probably taking too strong a view here, but the mathematics, it's largely driven by the mathematics as far as I know, which is in itself is not an objection as far as I'm concerned. A lot of what I do is driven by the mathematics. But the trouble with string theory is it's supposed to be a theory of the way the world operates. And if the number of dimensions of space is just wrong, I can't take it seriously.
Notably, not only rejecting string theory, but Sir Roger Penrose also questions the existence of dark matter and cosmic inflation. He even suggests that cosmic inflation is nothing more than a fantasy.
I never really felt happy with inflation right from the start.
But why does Roger Penrose reject Michio Kaku's string theory? Why does he say that cosmic inflation is a fantasy? And what made him still uncertain about the existence of dark matter? All this and more will be revealed in today's episode of Eyes 200M. Without further ado, let's get started. The history of science is filled with ideas, some of which have been shown to accurately describe reality over some particular range which we can probe it, and others of which turned out not to describe reality, although they could have if nature had answered our questions differently. We have a universe that obeys Newton's laws of motion and his theory of universal gravitation, so long as speeds are low compared to the speed of light. At higher speeds, Newton's laws of motion no longer apply and must be superseded by special relativity. In strong gravitational fields, even special relativity and universal gravitation aren't enough, and general relativity is required. Although general relativity holds up as our theory of gravity everywhere we've probed it, we fully expect that when we dive deep into the quantum universe, to small enough distance scales or at high enough energy scales, even general relativity is known to give nonsense answers that indicate an end to its range of validity, despite all of its predictive power and its status as arguably the most successful physical theory of all time. It's powerless to describe the region around a black hole's singularity, physics near the Planck scale, or the emergence of space and time themselves. For those phenomena, a quantum description of gravity will be necessary. Of course, we've never gotten anywhere near that far in practice. Directly, we can produce collisions in particle colliders up to a little more than 10 to the power of 4 giga-electron-volt, enough to unify the electromagnetic and weak forces and to create all the particles and antiparticles of the Standard Model, but still a factor of a quadrillion beneath the Planck scale. Whatever the physics of the early universe, the high-energy universe, or at distance scales below about 10 to 19 meters, we don't have any direct evidence supporting it. But that hasn't stopped us from, well, theorizing. We can concoct scenarios where new physics that, if we added it in, wouldn't conflict with the low-energy, late-time universe that's already been observed, comes into play. Many of these scenarios are quite famous within the physics community and include such novelties as extra dimensions, supersymmetry, grand unification theories, compositeness to certain particles presently thought to be fundamental, and string theory. String theory is perhaps the most controversial big idea in all of science today. On the one hand, it's a mathematically compelling framework that offers the potential to unify the standard model with general relativity, providing a quantum description of gravity and providing deep insights into how we conceive of the entire universe. On the other hand, its predictions are all over the map, untestable in practice, and require an enormous set of assumptions that are unsupported by an iota of scientific evidence. For perhaps the last 35 years, string theory has been the dominant idea in theoretical particle physics, with more scientific papers arising from it than any other idea. And yet, it has not produced even one testable prediction in all that time, leading many to decry that it hasn't even risen to the standard of science. String theory is simultaneously one of the best ideas in the entire history of theoretical physics and one of our greatest disappointments. Here's why. The story begins in the late 1960s, when particle accelerators were just entering their heyday. After the discovery of the antiproton in the 1950s, larger and more energetic particle accelerators began to be constructed, leading to an enormous suite of new particles that arose from colliding charged particles into other charged particles. The newly discovered particles came in three types: baryons, like the proton, neutron, and their heavier cousins; antibaryons, like the antiproton, antineutron, and heavier ones that matched one-to-one with the baryons; and mesons, which came in a variety of masses and lifetimes, but which all were unstable and quickly decayed away. But one interesting thing to note was that mesons, before decaying, were like bar magnets. If you break a bar magnet with a north and south pole, you don't get an independent north and south pole, but rather two magnets each with their own north and south poles. Similarly, if you try to pull a meson apart, eventually it snaps, creating two separate mesons in the process. This was initially where string theory began, as the string model of the strong nuclear interactions. If you envision a meson as a string, then pulling it apart increases the tension in the string until you reach a critical moment, resulting in two new mesons. The string model was interesting for this reason, but predicted a number of strange things that didn't appear to match reality, such as a spin-2 boson, which wasn't observed. The fact that the spin-1 state doesn't become massive during symmetry breaking, that is, there's no Higgs mechanism, and the need for either 10 or 26 dimensions. Then the idea of asymptotic freedom was discovered, and the theory of quantum chromodynamics came to be, and the string model fell out of favor. Quantum chromodynamics described the strong nuclear force and interactions extraordinarily well without these pathologies, and the idea was abandoned. The standard model, now complete, didn't need this new, esoteric and simultaneously ineffective framework. But a decade or so later, this idea was reborn into what's now known as modern string theory. Instead of working at the energy scales where nuclear interactions are important, the idea was put forth to take the energy scale all the way up to the Planck energy, where the spin-2 particle that made no sense could now play the role of the graviton, the theoretical force-carrying particle responsible for a quantum theory of gravity. That spin-1 particle could be the photon, and other excited states could be associated with the known standard model particles. All of a sudden, a long-sought dream seemed within reach in this new framework. For one, string theory suddenly made it plausible that the standard model of particles and interactions could be reconciled with general relativity. by viewing each of the elementary particles as either an open or closed string that vibrated at specific, unique frequencies, and the fundamental constants of nature as various states of the vacuum in string theory, physicists could finally hope to unify all the fundamental forces together. But what you get out of string theory isn't exactly as simple as this. You don't simply get the standard model and general relativity, but rather something much, much larger and more grandiose that contains both the standard model and general relativity, but also much more. For one, string theory doesn't simply contain the standard model as its low energy limit, but a Gauge theory known as N equals 4 supersymmetric Yang-Mills theory. Typically, the supersymmetry you hear about involves superpartner particles for every particle in existence in the standard model, which is an example of an N equals 1 supersymmetry. String theory, even in the low energy limit, demands a much greater degree of symmetry than even this, which means that a low energy prediction of superpartners should arise. The fact that we have discovered exactly 0 supersymmetric particles, even at the Large Hadron Collider or LCL energies, is an enormous disappointment for string theory. For another, string theory even in only 10 dimensions doesn't give you general relativity as your theory of gravity, but rather a 10-dimensional Brans-Dicke theory of gravity. You can get general relativity out of that, but only if you take the Brans-Dicke coupling constant to infinity and somehow remove 6 of those dimensions from relevance. If you've ever heard the word compactification used in the context of string theory, this is what it means: a hand-waving suggestion that somehow these extra dimensions and that additional parameter become unimportant. String theory, on its own, doesn't offer a compelling way to get rid of these extra dimensions or to make the Brans-Dicke parameter unimportant. And it must be unimportant. The original work that Brans and Dicke put forth suggested that a parameter of around 5 might be interesting. Modern tests of relativity have shown it must be greater than 10,000 or so. String theory also doesn't tell you what the values fundamental constants ought to have, since it offers no concrete way to calculate these string vacua that give rise to the fundamental constants. This includes the speed of light, Planck's constant, the gravitational constant, the coupling constants for the forces, the masses of the fundamental particles, the mixing angles of quarks and neutrinos, and the cosmological constant. String theory offers no clues towards calculating these fundamental values. However, the potential of string theory to even offer a possible quantum theory of gravity was what drew the majority of theoretical physicists to it, and the lack of solid alternatives have kept the field there. Despite the existence of 4 quantum gravity alternatives: loop quantum gravity, asymptotically safe gravity, causal dynamical triangulations, and entropic gravity, only string theory legitimately offers a true path, where all of the standard model is unified with gravity to that holy grail. However, the field is rife with problems. The correspondence between the aforementioned N equals 4 supersymmetric Yang-Mills theory and a string in a higher dimensional space is one of the biggest theoretical breakthroughs touted in string theory. And yet the space that it corresponds to is anti-de Sitter space, which predicts a cosmological constant with the wrong sign to agree with observations of our universe. There are a number of insights that string theory has offered into the problem of black hole entropy, but many argue that these have largely been oversold and that we don't understand entropy for black holes nearly as well as we claim to. And when you look at the explicit predictions that have come out for the masses of the mesons that have been already discovered by using lattice techniques, they differ from observations by amounts that would be a deal breaker for any other theory. Still, there are a large number of people who are drawn in by the mathematical allure of the theory. It incorporates concepts from quantum field theory, supersymmetry, grand unification theories, supergravity, extra dimensions, and general relativity, all in a single framework. Originally, there were many different string theories proposed, but mathematical advances have shown that they are all equivalent, or dual, to one another. However, every turn where we have looked for an observable that might be connected to string theory, in the sense that it would go beyond the standard model, we've come up empty. The cosmological constant is the wrong sign. Supersymmetric particles are nowhere to be found. Extra dimensions or a non-infinite Bronsdicke parameter have no evidence to support them. And the fundamental constants as well as the masses of the particles that exist in our universe have not been successfully predicted. The problem, as many see it, is that string theory was a very good idea, and people have a hard time abandoning good ideas no matter how fruitless their pursuit has been. Even though it didn't work out as a theory of the strong interactions, it provided the germ of what could become the holy grail of modern physics, a theory of quantum gravity that unifies general relativity with the standard model. So long as we don't have evidence that demonstrates string theory must be wrong, people will continue to pursue it. But disproving it would require something like demonstrating that no superparticles exist, all the way up to the Planck scale, something far beyond the reach of experimental physics today. We can all agree that string theory is interesting for the possibilities it holds. Whether those possibilities are relevant or meaningful for our universe, however, is something science has yet to affirm. Anyway, there are an unreasonable set of moving goalposts that some scientists, particularly contrarians to the mainstream, set up to add a false legitimacy to their claims, as well as a disingenuous uncertainty to the well-justified consensus positions. We do not need to identify the exact mechanism of baryogenesis to know that a matter-antimatter imbalance came about in our universe. We do not need to directly detect whatever particle is responsible for dark matter. Assuming dark matter even is a particle with a non-zero scattering cross-section to know it exists. We do not need to detect gravitational waves from inflation to confirm inflation. The 4 discriminatory tests we've already performed are decisive. And yet, there are still unknowns that we must be honest about. We do not know the cause of baryogenesis or the nature of dark matter. We do not know whether inflation really must go on for an eternity, whether it really began from some non-inflationary predecessor state, and we cannot test whether the multiverse is real or not. We do not know, to put it bluntly, how far the range of validity for these theories extends. But the fact that there are limits to what we know and to what we can know does not make our actual knowledge of the cosmos any less certain. Sympathy for contrarian positions and excitement about speculative ideas should only extend so far, to the extent that they're supported by the full suite of available evidence. Especially when you're attempting to push the frontiers of science forward, it's important to not lose sight of what is actually solidly known and established along the way. After all, as Richard Feynman put it, when it comes to science, if you don't make mistakes, you're doing it wrong. If you don't correct those mistakes, you're doing it really wrong. If you can't accept that you're mistaken, you're not doing it at all. Next, let's shift the attention to dark universe. Dark energy is thought to comprise roughly 68% of the known universe, and dark matter 27%. Yet, we only know about them in terms of gravity. In other words, scientists can only detect them indirectly, by how they cause stars and galaxies to move and behave. For instance, the amount of matter inherent in galaxy clusters alone doesn't account for the gravity that keeps them together. Some other force must be involved. Here, dark matter is the most common answer. Astrophysicists have been postulating the existence of dark matter for about a century. Swiss astronomer Fritz Zwicky was the first to see that there was far more matter in the universe than we could directly observe. Though he postulated this in 1933, U.S. astronomer Vera Rubin made the concept more popular in the 1970s, when she used it to try and illustrate how stars move and at what velocity. Australian and U.S. astrophysicists won the Nobel Prize in Physics in 2011 for their 1998 discovery of the Hubble constant. This is the rate at which the universe expands. Since then, despite many attempts to detect dark matter and dark energy, no progress has been made. As a result, a group of scientists, including Sir Roger Penrose, reject the dark matter hypothesis as implausible. Instead, they believe that the accepted laws of physics are incorrect. According to them, either the laws governing the motion of astronomical objects are wrong, or our theory of gravity doesn't work on galactic scales. For both conjectures, these researchers have developed an array of new physics theories, governed by different equations than those taught in physics classes. Both camps, the dark matter proponents and the modified physics community, point to different sets of astronomical data to support their position. And both groups can point to observations that support their conjectures and disfavor the other. While most astronomers embrace the idea of dark matter, André Maeder, honorary professor in the Department of Astronomy at the University of Geneva, has a radical theory that's shaking up astrophysics. He says neither dark matter nor dark energy exist. These concepts, he believes, are no longer required. The Swiss physicist can demonstrate how the universe works without them. His findings were published recently in a series of papers in the Astrophysical Journal. So how does this new model work? It all surrounds what's known as scale invariance. This is when the properties of something do not change no matter how you measure it, regardless of scale. We can multiply their energies or lengths by whatever number, and they do not change. Certain fractals, for instance, if we zoom in or fade back, remain the same size and shape. Their properties don't change. The same is true of empty space. Whether you pan out or in, it's the same. This isn't exactly foreign to physics. Scale invariance is actually a fundamental part of the theory of electromagnetism. Maeder proposes that instead of dark matter or dark energy, we've simply forgotten to include scale invariance into the standard model, our current model of the universe. This has so far been developed mainly from Newton's universal gravitation, Einstein's general relativity, and quantum mechanics. Maeder said, "In this model, there is a starting hypothesis that hasn't been taken into account, in my opinion. By that, I mean the scale invariance of empty space. In other words, empty space and its properties do not change following a dilatation or contraction. If this is true, it would change everything we know about gravity and universal expansion. What's different is that Einstein believed empty space operated on what's known as the cosmological constant. Today, we'd interpret it as a form of dark energy. Maeder's model instead includes scale invariance in empty space. He tested his hypothesis on the accelerated expansion of space, and it worked without the need for dark energy. He also applied it to galaxy clusters. Their behavior was in line with Maeder's calculations. In another test, Maeder showed that he could account for why stars in the outer reaches of galaxies move faster than those within them. Dark matter is the usual explanation. Lastly, he accurately illustrated the dispersion of certain stars as they travel through the Milky Way, which until now has been difficult for astronomers to understand. These findings are controversial. The Frankfurt Institute's Sabine Hossenfelder, a physicist blogger, called Maeder's hypothesis inconsistent, while astrophysicist Katie Mack of Australia's University of Melbourne said it's been massively overhyped. There's other evidence for dark matter, she said, in the cosmic microwave background, the residue of the Big Bang. It's also present in how galaxies are distributed. Finally, a phenomenon called gravitation lensing also hints at dark matter. Though there are other ways to interpret Einstein, that doesn't mean they're true, Mack said. Until Maeder's hypothesis is proven across a number of observations and measurements, his theory won't supersede that which is already in place. But if he succeeds, it'll be a paradigm shift in our entire understanding of how the universe operates. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.